Hello, today we're going to have a look at Gaussian integers, and then we'll prove that there are infinitely many primes of the form 4k plus 1. And we'll do that using the Gaussian integers and somehow mimicking the proof that there are infinitely many primes. Okay, so let's start with a motivation for the Gaussian integers. So let's look at the first couple of primes. So these are the first ones, and now let's see which one we can write as a sum of two squares. So 5 is 4 plus 1, and similarly, let's see which else. So this is 9 plus 4, and also this is 16 plus 1. And you can also check that you can't write 3, 7, 11, 19 as a sum of two squares. So you just have to check some numbers and see that they don't add up to give these prime numbers. Okay, and now let's have a closer look. So 3 is of course 3 modulo 4, 5 is 1. I won't write the modulo 4 everywhere, but it's all, we look at it every time. Modulo 4, so that's 3, that's again 3, that's 1, that's 1, and that's 3. So we see a pattern here, and this pattern is actually true for all primes. So let's state the following theorem. We won't prove it, but we'll state it. So an odd prime p is the sum of two squares if and only if it's 1 modulo 4. So p is 1 mod 4. Okay, and now let's look at it in a different way. So we couldn't write 3 as a sum of two squares, but we could write 5. So let's write it in another way. So we'll write it as 2 plus I times 2 minus I. Let's check that this really gives us 5. So this is 2 squared. Then we have 2, so minus 2i plus 2i and minus I squared, so that's 5. That's good. And let's make another example. So 13 is 3 plus 2i times 3 minus 2i, and you can again check that the equality is true. And as you already saw probably, so here we have 2, here we have a 1, here we have a 2, here we have a 1i, here we have a 3, 2i, and that holds in general. So we can rephrase this, that so this basically, we'll come back to this later, but this motivates the following definition. So now we'll define the Gaussian integers. So we call them C adjoint I, and they are just as a set, the subset of the complex numbers, and of course they have a group structure and even a ring structure. So that's just a plus ib, where a and b are integers. Okay, so that's the Gaussian integers, and now we'll use our observation from before. So this observation and to state the following theorem, which again we won't prove, but we'll use it later. So at first the claim is that this is a Euclidean domain. So the Gaussian integers are a Euclidean domain. So that means it's an integral domain. We have some division with remainder, and then also this implies that it's a principal ideal domain, and in particular it's factorial. Okay, so let's have a look at the units of this ring. So the units are just the invertible elements, so that's 1, -1, I and -I. And now let's have a look at the primes. So as it's a principal ideal domain, we can have a look at the primes, and we have three kind of primes. So if you know some algebraic number theory, probably you already know all of this, but let's state it for convenience. So the primes up to units, of course we can multiply with a unit and we still have a prime. So the first kind of prime is there's just one of this kind, that's 1 plus I. So up to unit there's 1, if we include unit there's 4. So if we have, so this corresponds somehow to 2. In algebraic number theory we would say that it ramifies, but you don't need to bother about knowing this. So that's just minus I. So let me show why it's related to 2. So plus 2I plus I squared. So if we multiply with the unit minus I and we square it, we get 2. Okay, now let's look at another kind of primes. So we take primes p in the integers, where p is 1 modulo, not 1, 3 modulo 4. So that's, for instance, 3, 7, and so on. And so we've seen them before, so these are the ones we can't write as a sum of two squares. And now we come to the primes in the integers, which we can write as the sum of two squares. So we get 2 primes in the Gaussian integers, the prime and its conjugate. So these are primes where the prime times the conjugate is a prime in the integers. And so this is prime, and it should be 1 modulo 4. Okay, and let's also give some examples. So let's take p to be 2 plus I, the conjugate to be 2 minus I, and then p times p conjugate is 5. And another example would be, as we already have, so we've seen both of them before, so 3 plus 2I, p bar to be 3 minus 2I, and then we get 13. Okay, and of course there are also more examples of them. Okay, and now we're gonna prove that of this third kind that we have infinitely many. So the theorem says there are infinitely many primes of the form 4k plus 1, And so as the primes of the form 4k+1 correspond to these primes, it's enough to prove that there are infinitely many primes of this kind in the Gaussian integers. So the statement here is about primes in the integers, but we'll prove a slightly different statement which is equivalent. So P and P bar in the Gaussian integers with P times P bar is P. Okay, and also a short remark about this statement before. Of course, if we have different prime numbers in the integers here, then also these P and P bar will be different. Okay, so let's prove it. I mentioned that we want somehow to have a similar proof as the classical proof from Euclid, that there are infinitely many primes. So let's suppose it's not the case. Then we take the product of all of these P and P bar. So and also we're gonna multiply it with 1 plus I. Okay, so what do we get? 1 plus I. Let's call these primes pi and the conjugates of them. So we get pi times pi bar. And that's, well, 1 plus I. And then some product of some pi in the integers. And that's just the product from 1 to n of the pi plus I times this product. Okay, so that's how we start. Next, we add 1. So that's also similar as in the classical proof. So let's call this number n. And this is just 1 plus this product in the real part, and as the imaginary part, just the product. Okay, and now we can easily see, as in the case of the classical proof, that 1 plus I, P1, P1 bar, and so on up to Pn, Pn bar, they don't divide n. So if they would, we would have that they divide. They divide n minus 1. So why is that? Well, this, where do we have it? This number here is n minus 1. And they divide all the factors in n minus 1. So, or maybe this is also n minus 1, so here it's clearer. So they divide all the factors. So they divide n minus 1, certainly, and if it would also divide n, then they would divide 1. And that's not true. So we have that these factors don't divide n. And now we get that n has to be a product of the form, so some product of some j, pj, where the pj's are 3 modulo 4. So, and this of course is just up to units. So we can always multiply with a unit. But this would give us that n is either in the integers, in z, or it has to be in I times z. But that's clearly not the case. So the real part of n is bigger than 0, so it can't be in IC, and also the imaginary part is bigger than 0, so it can't be in C. So that's a contradiction. And this tells us that our assumption was wrong. And indeed, we have infinitely many primes, p bar, in the Gaussian integers of this third form here. And therefore, we have infinitely many primes of the form 4k+1 in the integers. Okay, thanks for watching. Have a good day and bye.